Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about how to convert between different coordinate systems or different coordinate bases, if you will. You will recall that I introduced in my previous video a set of coordinate systems that are kind of, you could think of them as like the common used coordinates for physics. So recall that we had 2D coordinates, 2D coordinate systems or bases had the possibility of being rectangular, or in other words Cartesian, or they could be polar or circular if you prefer. So rectangular, circular, which is sometimes more frequently called polar. And then in 3D coordinates, the ones that we typically use again in physics, especially in these introductory level courses, if we go to 3D at all, there's the Cartesian system, which is essentially cubic. So we could call this cubic if you'd prefer. There were the cylindrical. Cylindrical is spelled this way. And then there was the spherical. And I basically just kind of showed how to do rectangular, circular. I didn't really try to draw these others, A, because we don't use them very much in an algebra-based physics course, and B, because I'm not very good at drawing, and drawing them in 3D was probably just going to confuse people. Today, what we want to do is learn how to convert from one to another. In other words, how do we express a vector which is given in, say, rectangular Cartesian as a vector in circular or polar coordinates. So in 2D, what we would have is essentially an XY plane, so Y and X, and then your vector generally is just a point somewhere in that XY plane that the vector points from the origin to. Now bear in mind that this vector that I've drawn here and a parallel vector, so if I copy this and then paste it to here, or paste it to here, or here, or here, these are all considered to be basically the same vector. They're all pointing the same direction. They all have the same magnitude. This is still the same vector. This one down here, same vector. These are all same vector. But that aside, we just want to use a simple system. We'll draw our vector one more time. Oops. And this time we will just kind of move it over to here. Hello. So we have only this one vector, and we'll label kind of where does it fall on the X and Y axis. So we've labeled the axis X, we've labeled the axis Y. That makes this distance right here essentially our X distance, and this distance right here our Y distance. The overall vector, however, has a set of polar values. Let's do them maybe in purple for polar. There's a theta, and then there's a length lowercase r. And this entire thing could then be redrawn as a sort of right triangle. Maybe I should once again actually just paste my vector and then move it over here, maybe. And then I could draw onto it the x and y parts. So the x part here and here. This is the x part, this is the y part. These make a right angle with respect to each other. So what I have here is a complete right triangle. The interior angle to that right triangle is angle theta, and the hypotenuse has length r. So given what we know about right triangles, it follows that we should be able to write something along the lines of x squared plus y squared is r squared. That's Pythagorean theorem. So x squared plus y squared is equal to r squared. And along similar lines, if I take the tangent of the angle theta, that's going to be y divided by x. And so what these two equations tell me are that r is equal to square root of x squared plus y squared, and that theta is equal to the arctangent, or sometimes also called inverse tangent. It's the tan -1 button on your calculator, of y divided by x. Okay, so that's how you convert from Cartesian to polar in 2D. So this converts from Cartesian to polar. And again, that is if you are working in... Now, there is a little bit of a caveat to all this. Strictly speaking, as written, what I've told you is correct no matter what quadrant you're in. However, not all people's calculators are created equal. Some of you may be lucky and you have a calculator that if it's in, let's say, the second quadrant and you enter a positive value for y and a negative value for x, you'll then take the inverse tangent, and if you write all that onto one line, it'll spit out a number that's between 90 degrees and 180 degrees if you're in degree mode. Others are not so lucky, and if you do that, it will simply spit out a negative number essentially between 0 and 90 degrees. So it'll say like this value is negative 15 degrees or something like that. So you have to be able to know how to convert it into, essentially any of the quadrants that you get. So one way of dealing with that is as follows. Suppose, for example, that your vector happens to look like this. Well, basically what you do in this case is you can again set up a value for y, which is positive, and a value for x, which granted is negative, but let's treat it as a positive number for right now. Your angle theta is actually this angle right here. This is theta, this side right here is r. Now finding the value for r doesn't change regardless of the quadrant. You just square x, you square y, you add them, you take a square root. Even if they have negative values, when you square it, that negative value goes away, and r, it should be noted, has the positive value of this square root. So we could say r is equal to plus of the square root. Theta in this case may not give you the right answer if you plug in your y and your x into your calculator. So what we do is we make kind of like a dummy angle. I'm going to call it beta. Beta rhymes with theta. We'll call this dummy angle angle beta. Well, looking at this right triangle, you can see that the tangent of beta is again equal to y divided by x. Now I've chosen beta to be the angle that the vector makes with respect to the x-axis. Okay. So this lets you find an angle beta. Tangent beta is this, therefore beta is the inverse tangent of y over x. And note again that I'm making these both be positive valued. So plus and plus, plus and plus. Even though x in this case is negative, we're taking like an absolute value. So if you'd prefer, you could say something like tangent beta is equal to absolute value of y divided by absolute value, of x. Now, this gets you this little angle beta, but you got to convert it into an angle theta with respect to the x-axis, or maybe you're told to find with respect to some other axis. We're going to do it with respect to the x-axis for consistency though. Well, in this quadrant, quadrant 2, theta is equal to 180 degrees minus beta. Quadrant 1, that one just simply has theta equals beta, so you don't have to do this process if it's here in quadrant 1. Quadrant 3 means it's down here somewhere, and again we're drawing this always with respect to the nearest x-axis. Theta in this case would be 180 degrees plus beta. And then in quadrant number 4, theta would be 360 degrees minus beta. I appear to have misspelled quadrant in my haste to write the word quadrant. Okay. So note that again, beta is always, in this case, beta is always angle with respect to the plus or minus x-axis, whichever one is closest. So this basically means that 0 will be less than or equal to 90 degrees, will be less than or equal, will be less than or equal to beta, will be less than 90 degrees. Okay, so that's converting to polar. What about converting to Cartesian? That part's actually more straightforward. To convert from polar to Cartesian, just note that the sine of angle theta is equal to opposite, that would be y, divided by hypotenuse r, and that the cosine should be adjacent, that's x, divided by hypotenuse r. It follows, therefore, that you can get x and y by rearranging these two equations. And by the way, theta can range from 0 to 360 degrees. You'll get the right answer. We'll see if we can do an example here. So Stan is walking 300 paces east and then 400 paces south. And we want to know if somebody else were to start at the same place that he started from, what direction and how far would they have to walk to go in a straight line from where he started to where he ended. As always, it's a good idea to try to draw some sort of picture or diagram to help us solve our problem. So we have the east-west axis and we have the north-south axis. Now, according to the story here, Stan walked 300 east, so that would be walk 300, and then 400 paces south, walk down here, 400. And so our net displacement for Sam would be this right here. So this right here has some value r, and it has some angle theta, which we might re-specify in terms of, say, a beta or something like that. So here's our beta. All right, to get the magnitude, we would use r squared is equal to the east distance squared plus the south distance squared. Okay, or in other words, r is equal to, or distance is equal to, east squared plus south squared square rooted. So therefore r would look like the square root of 300 paces squared plus, if we want to be really pedantic, we'd put in the negative sign and say minus 400 paces squared. If you square those two numbers, you add them together, and then you take a square root, you will get that r is 500 paces. So the magnitude r equals 500 paces. What about the direction? Well, the tangent of beta is equal to opposite, that would be 400, divided by adjacent, that would be 300. So that means that beta is the inverse tangent of 4/3. That comes to approximately 53.1 degrees. So 53.1 degrees. So direction, we could call that 53.1 degrees south of east. We could also call that, in terms of the xy direction, 306.9 degrees. So this would be let's call it 306.9 degrees counterclockwise from east. Now obviously if you're using a compass, this top answer, 53.1 degrees south of east, is the answer that actually makes sense. But if you're doing like an XY and you want to have from the x-axis, you'd have 306.9 degrees. Okay, so that's it. That's all I'm going to do in today's video. Hopefully you learned something from watching it, and in the meantime, thanks for watching.